Uh, Today, Professor Mark Powell will give a talk about classification of four manifolds and the double star construction. Let's welcome.
Okay.
Please start. Yeah.
Yeah. Thank you very much for the invitation, and thank you for thanks for coming. So yeah, I'm going to talk to you about these topics. So I want to start off by I'm going to talk about classification of four manifolds in a bit of generality. Starting off with I want to in the first section is about what we know about the homotopy classification of four manifolds. So by this I mean we want to decide, given two four manifolds, whether they're homotopy equivalent. So, and then I'm going to talk about that in some generality, and then I'm going to specialize to the case of fundamental group D infinity. So the infinite dihedral group, which is the same as the free product of two copies of Z12. I want to talk about the homeomorphism classification of such four manifolds, and then there's a couple of particular four manifolds within this homotopy classification that are homotopy equivalent but not homomorphic, that I think is a really cool pair of examples, and I want to talk about those in some detail. And they've got names. One they're called. I mean, there's a four manifold called E that I'm going to talk about, and in one of the four manifolds is E connect some E, and then there's another four manifold which is called star E, and then this is called the star partner of E, and I'll talk about what this means. And then I said the connect sum of two copies of this with itself, and these are going to be homotopy equivalent, but not homeomorphic. And so I'm going to tell you about these. And Seongjong, apologies if I'm saying that wrong, told me that he was interested in things to do with dual spheres. So this is an example where dual spheres in four manifolds show up.
Excuse me, and what is star?
Star is I'm going to tell you what's well. You should just think that star E is a different manifold that's homotopy equivalent but not homomorphic to E. So there's something called the star construction that gives you a new four manifold, and I'm going to tell you what that is. This is I'm just giving you an overview of what the talk is about. So
are all these manifolds smooth underneath?
Well, that is what I'm going to tell you about. So this is No, in general, I'm going to just talk about topological four manifolds. They don't have to be smooth. But this E is a smooth manifold. So the connect sum is smooth. This is a topological manifold that's not smoothable. And then one of the theorems will be that, in fact, this connected sum is also smooth. But that's very far from obvious. Under this construction of it is as a topological manifold.
Thank you.
So, yeah. So I want to try and explain to you why this is a smooth manifold. So that's kind of the okay. So that's just an overview of what's going to happen. So let me get started. So in general, X is going to be a closed orientable manifold. Right, so because I didn't write smooth then, that's because it doesn't have to be smooth necessarily. And then in order to talk about the homotopy classification, we need to talk about invariance. So one of the key invariants that we look at of homotopy classification is what Hamilton and Craig called the quadratic two type. So this is a quadruple consisting of the fundamental group, the second homotopy group. So those sort of very standard invariants. There's something called the K invariant, and then there's the equivariant intersection form. So I need to tell you a little bit about what these two are. So the Kx is an element of the third homology of pi1 of x with coefficients in pi2 of x. Thinking of this is a z pi1 of x module, and the idea is, I mean, we have a space X, and it comes with a map to its Poznikov 2 type. So this is a space that has homotopy it has non-vanishing homotopy groups in degrees 1 and 2, and all the rest of the homotopy groups, pi3, pi4, etc., are all 0. So it's sort of like a bit like an Eilenberg-MacLane space, but it has non-vanishing homotopy groups in 2 dimensions, 1 and 2. But nowhere else. You can make one of these things by taking your given X and adding on cells iteratively to kill the higher homotopy groups, one at a time. And this fits into a short exact sequence where we have the Eilenberg-MacLane space, and so pi1, k pi1, 1 and k pi2, 2. This fits another short a vibration sequence. That's what I should have said. You get one of these, and there's a unique obstruction to getting a section of this thing, and that's if you do obstruction theory on this, then the obstruction that you get is this. So so this is the obstruction. To a section of this vibration, and it's sort of what tells you. But if you want to know about the homotopy type of this Poznikov 2 type, then you need to know about pi1 and pi2 as a pi1 module, and then you need to know about the how they fit together to build this space up to homotopy equivalence, and that's what this K invariant tells you. And then there's the final thing, which I call lambda x, is the equivariant intersection pairing. So given 2 elements of pi2 of x, I think about those as immersed spheres in my manifold, and they intersect in a bunch of points. There's 1, 2 sphere, and here's another one, and they intersect in some points, and each of those points gets a sign, and it gets a group element in pi1 of x, because I can start at the base point. Here's my base point. I can start at the base point. I can go in one of the 2 spheres to the double point, and then back in the other 2 sphere to the base point, and that gives me a loop. So that's where I got this G from. And so this thing is, then I sum those up over all the double points, and I get an element in of the fundamental group. So those are the sort of the fundamental invariants in this quadratic 2 type. Okay, any questions about those invariants? And I've tried to introduce them.
Maybe you can give some examples how to calculate lambda invariant.
Or how to calculate the lambda invariant. Yeah, so it sort of depends. That could be that could be quite tricky in general. I mean, one thing you might do is if you well, let me just start off with what can I do? Well, we'll do if your form manifold is given to you by a Kirby diagram. Does this make sense as a description of a form manifold? This is supposed to be CP2 plus S2 cross S2.
Okay.
And And now I could say, okay, I mean, this is sort of an easy example because there's no one handles. So each of these two handle attaching maps corresponds to an element in, so this is my x, and I'll now see h2 of x is z cubed. Now I can, so I think of this, here's a 4-ball, and I've got these 3 2 handles like this attached. And so now the if I take the core of the 2 handle of each of the 2 handles together with null homotopies in the 4-ball for each of these 2 handle attaching maps, then I get a then I get a representative for that class in H2 of X corresponding to each of the handles. And now if I take if I were to count the intersections between these things, maybe I should leave a gap there. If I can figure out what the null homotopies look like, and I can understand null homotopies of these things into the 4-ball by doing an unlinking procedure on this link, right? I just have to do a crossing change here, and then I've got an unlink, and so I see that I have to get I get a single intersection between these 2. Maybe that was here, and then this one doesn't intersect anything, so maybe I should have that one off by itself. And then there's one extra thing you have to think about for so this tells me that when I write down the matrix, I get I'll just ignore the off diagonal entries, but I get because these 2 intersect, I get 1s there, and because nothing else intersects, I just get 0s here. And then the other thing is the self-intersection numbers come from taking a homology class and pushing it off itself. And the fact that you push it off here with framing 1, meaning differing from the Seifert framing by 1, means that you, well, let's see. Which way around does it go? To go that way around with my right hand. And then, so I read now to understand the self-intersection numbers, I have to now do an unlinking procedure between the green and the white. And that's also going to involve one intersection point. So I get a 1 here, and then because those are 0s, I get 0s. So you can sort of read off at least if you were given the 4-manifold in such a way, then you could read off the intersection pairing. And it's a bit more complicated when you've got 1 handles, because then you have to figure out which linear combinations of the 2 handles actually give rise to cycles. And then, but in principle, the same computation is feasible. Okay, I don't know if was that somewhat helpful to some people. Feel free to press me for more on that. But I'm not really claiming that these things are easy.
Okay. You just wrote the quadratic form and how to calculate lambda.
Yes. Well, yeah. In the case of a simply connected manifold, this is the this is isomorphic to H2 of X if pi1 of X is 1, and so I did a simple example in that case. Sorry, yeah, I put it H2 because it's equal to pi2 in that case. So I did that in my head without saying. Apologies. So this is like the intersection form, but it's the equivariant version in the when you've got non-trivial pi1. And this need not be a free module in general, so it's more complicated. I'm not saying that this is always sort of a very easy algebraic stuff to understand and work with, but it's sort of fundamental data that one has. tell you the key theorem about it. So this is due to Bowers and Bleiler, and then also a bunch of people that I'll say below. Let's take x and x prime as above. Then every isomorphism. So suppose that you can imagine these tuples of invariants are equal in some sense. So what exactly an isomorphism here means is a little bit involved. You have to have an isomorphism of the pi1, and then once you've got an isomorphism of the pi1, you want an isomorphism of the pi2 as a z pi1 module, intertwining the given isomorphisms of the fundamental groups. And then once you've got isomorphisms between the pi1 and the pi2, you can identify the two groups in which the k invariants live, and then you want that to send the one k invariant to the other. And then again, once you've identified pi1 and pi2, you can consider isometries between the two intersection pairings. So that's what I mean by, there's a notion of isomorphism between these tuples that I just tried to describe. And if we have such an isomorphism, then it's realized by a homotopy equivalence. I'm provided. So this is only known for certain fundamental groups, provided pi1 of x is well, first case was trivial. This goes back to Whitehead and Milner from the 40s and 50s. I1Z, I believe, I mean, it certainly follows from Friedman Quinn. I'm not sure if this was done earlier by someone else actually, but I mean they did the homomorphism classification from which the homotopy classification follows. Then certain finite groups, so finite Y1 if the cohomology is 4 periodic, repeats once when the star goes up by 4. And this was Hamilton and Craig. Yeah, hello.
Yeah.
I'll ask a question. So for the Hamilton crack, is that just that there's a finite number of types?
A finite number of.
Yeah, can you say a few more words about the Hamilton crack theorem?
Oh, I mean here I mean finite if it's a finite group. So yeah, so if given a finite group with 4 periodic cohomology, then the homotopy type is determined by the quadratic 2 type. So, yeah, I mean there's different. So finite cyclic groups, or these some quaternionic groups, I think also fit into this. I mean, finite cyclic groups are 2 periodic, but then I think some of these quaternion groups are 4 periodic. The other family of groups, then the sum that we did could be two generator abelian groups. So if it suffices to use 2 generators to generate your group, and this was That was joint work with Daniel Kasprowski and Ben Ruppick. Then dihedral groups. I mean, finite dihedral groups. That was work of Kasprowski, Nicholson, and then Ruppick. And then so the most recent thing is we extended this to fundamental groups of three manifolds, at least many three manifolds, closed orientable three manifolds with where we have to restrict to every finite subgroup. And that's soon to appear work with Jonathan Hillman and with Daniel again and with Aru Ray. So there's a bunch of fundamental groups where we know that the homotopy classification is given by this quadratic 2 type, and there are also some groups where we know that it's not. So there's definitely groups of the form Z cross Z mod P where the quadratic 2 type does not suffice. So we know it's not true in general, but we've been trying to sort of prove it for as many groups as we can. Okay, so that's sort of a just an overview of some of the things we know about quadratic homotopy classification. I don't want to go into how you prove these things, so I'm just gonna skip that and leave that as a fact. I want to instead restrict to the infinite dihedral group. So this is, I mean, this is a special case of this theorem, because if I take the connect sum of two copies of RP3, that's suddenly a closed orientable three manifold where finite subgroups are cyclic. So so the pi1. Well, so when you look at this, you see that the fundamental group is Z2 star Z2, which is isomorphic to this infinite dihedral group. So of course this you may be right as X, Y.
Excuse me, may I have a question?
Yeah, hello.
What's the definition of the D infinity?
Oh yeah, let me tell you. I was about to tell you. So remember that maybe worth remembering that. Well, everybody. I mean, if you like, the definition is the free product of Z2 with itself. That's a perfectly good thing. But maybe it helps to fit it into the other dihedral groups. So I know everybody probably disagrees about what the definition of what the notation for the dihedral group is. I always found it. I always decided to use the. I write the number of elements in the group, but you may call this Dn and not D2n. I wouldn't.
Oh.
Judge that. So this has a reflection, a rotation and a reflection, and r to the n is trivial, and s squared is trivial, and if I conjugate r by s, I get its inverse. So if you want to get the infinite diagonal group, you just make the rotation be infinite order. So this is rs, where we have s squared and s rs equals r inverse. And it fits into a short exact sequence like this. Where this is generated by the R, and this is the reflection. And what's good about this is that it means the group is good. So if you can classify manifolds up to homotopy equivalence, then you have a chance of trying to classify them up to homeomorphism if your group is good. So if and good means so that's good in the sense of Friedman, and it means that that surgery you can hope to apply high dimensional surgery theory in dimension 4, which makes me very happy. And then those are called the good groups. And one of the groups that are good are finite groups are good. Z is good, and it's also closed under extensions. So since this is a finite group and this is Z and it's closed under extensions, then this means that the infinity is a good group. And that means that we can use the Browder-Novikov-Sullivan-Wall surgery theory to attempt homeomorphism classification. Right, I'm not necessarily expecting you to know all about surgery theory. You don't have to. I'm just mentioning it as being this method that is going to enable us to, or does enable us to do this computation. So we want to sort of improve in this particular case, improve the homotopy classification to a homeomorphism one. So I need to tell you some more invariants. Well, maybe two invariants. So the first one is every four manifold has a Kirby-Siegmann invariant. This is the Kirby Siegmann invariant, which is Z2 valued, and this is an abstraction for the tangent bundle, or the topological tangent bundle. Every topological manifold has a topological tangent microbundle, and we want to know whether the bundle can be smoothed. So whether you can, well, in fact, just there's a stable version of the bundle, and we want to know whether the stable version of the bundle can be sort of improved to one with transition functions with linear transition functions, so which in the end would mean living in the orthogonal group. as opposed to just transition functions given by homeomorphisms of Rn that fix the origin. So a priori for a topological manifold, the transition functions would just be homeomorphisms of Rn that linear, then your then this curve is even invariant vanishes. That doesn't mean that you have a smooth structure on the manifold. It's just an obstruction to getting a smooth structure on the manifold.
So this would apply to like orbifolds?
Oh dear. I'm not sure about that. It probably. I'm not
Go
entirely
ahead,
sure.
go ahead, keep going.
That's an interesting question, but I haven't thought about it. Yeah. Well, I'd be happy to discuss that afterwards, but I don't actually know. Okay. So what's next? Oh yeah. So then there's this other invariant. So so we're going again. So X is going to be again closed, oriented, and it comes with a map. We're going to fix a map alpha from the fundamental group to the infinite dihedral group. And now we have to think about the second Stiefel-Whitney class. So if the second Stiefel-Whitney class of the universal cover, so when I write the tilde there, I mean the universal cover. If that is non-zero, then I'm going to set. So I'm now going to define something called S. So S of X alpha, and I'm going to set that to be 0 in this case. But now things have become more interesting if there is a spin structure on the.
Can you formulate your main result of today's lecture?
Well, I'm building up to it. Well, there's a couple of main results. Well, I've told you the first one, which was the homotopy classification. The next result will be that I'm going to tell you about the homeomorphism classification with infinite dihedral fundamental group. For that, I need to define invariants. The homeomorphism classification is going to be in terms of the invariants that I'm describing now. So I need to define the invariants, and then I'll be able to formulate the result in terms of them. Is that all right, or do I need to do it before? I could write the result before I've defined them, I suppose, but it just seemed perverse to me. And then, yeah, and then there's one more result that I'm going to mention about the examples with E that I mentioned at the beginning. So, I mean, I'm going to keep defining this invariant, and then once I've defined it, it's an invariant of 4 manifolds with infinite dihedral fundamental group. And then I'm going to state the theorem involving them. So if I have this map to D infinity, remember this is Z2 star Z2, then the classifying space for Z2, the Eilenberg-MacLane space KZ2, 1 is RP infinity. This is K Z02, 1. And so if I have the free product, then the Eilenberg-MacLane space is a wedge product of the two things. But I can up to homotopy equivalence, I could change the wedge product, and I could instead write it. I could sort of take the take the wedge point and just expand it to an interval. So here's an RP infinity, and here's an RP infinity. And so I get this map here, this alpha, determines a map to this space. And then I'm going to define S be the inverse image of a half. So a half lives in the interval 0, 1, of course. And this is a subset of X. Well, the universal cover maps to here, and this thing lifts to the universal cover, and so we get this inclusion gives us an induced spin structure. So this becomes a spin 3 manifold, and then I can do. I take my my X and my S, and then I break it up into X sub L and X sub R by cutting it along like this, and then now I have to let N be a spin manifold with boundary of N equals S, and then I can form M sub X sub L and N, or N X sub R. And so this is going to be called P sub L, and this is going to be called P sub R. So I'm just doing a construction of some 4 manifolds like this, and then S of X alpha, which is going to be this is an element of turns out Z2 cross Z2. This is now given by the signature of this PL divided by 8 plus the Kirby-Ziemann invariant of it. That's the element of Z mod 2. And then I just do the same thing with the right. L is for left and R is for right. So I do this divided by 8 plus the Kirby-Ziemann invariant. And this is taken mod 2. Mod 2. Mod 2. So everything's in Z mod 2, and I get an element of S2 cross S2. Okay. So that's maybe slightly mysterious, but this is it turns out that this is an invariant of the homomorphism class of such 4 manifolds. So I can formulate the theory. Okay. So let X1 and X2 be closed oriented 4 manifolds with maps alpha I so they're going to come with maps to D infinity. Then X1 and X2 are orientation preserving homeomorphic over D infinity if and only if. Well, we need them to be homotopy equivalent, so we need their quadratic 2 types to be isomorphic. We need their Kirby-Ziemann invariants. 1 or 2. We need the same, and we need their these S invariants that I just defined to be equal. So there's the homotopy classification. There's this Kirby-Ziemann invariant, which is just always going to be a necessary condition for homomorphism. And then there's this one extra invariant that's required, which I just defined over here. By the way, this thing here is due to And the definition of the invariant appeared in a paper of Craig, Look, and Titan. So they define the invariant. Our theorem is that this gives the final step in the classification, of the homeomorphism classification of these manifolds. Once you know the homotopy classification. Okay. You guys have questions? Did I? No. At least I answered the previous question.
I was writing, so I missed the OP.
Oh, orientation preserving.
Oh, thank you.
I'm trying to make that a thing. So I'm glad you asked about that. You know how people, if you say FG free module, everyone knows that means finally generated. Yeah, it's my dream to make OP be a thing so that you don't have to keep writing orientation preserving. So yeah.
For now, I have to.
Everyone start using that, and I'll be pleased. Because you have to, well, it sort of makes sense of the intersection that when you define the equivariant intersection form, you have to pick an orientation in order for that to be well defined and not just well defined up to sign. So then when I talk, I mean, it could be that I have a form manifold where the Q of one is the same as the Q of the other one, but with a minus sign, and then, well, that would be annoying. So so just to sort of make life simpler, I'm going to fix an orientation, and I'm only going to ask for orientation preserving homomorphisms. You can drop the orientation and you can figure out how it works without require. You just have to have an extra couple of cases. But to make a cleaner statement where all the invariants are well defined and I'm just asking for an isomorphism of the invariant, it's better to just stick with everything oriented and ask for orientation preserving homomorphisms. To avoid, otherwise you tie yourself in knots with all these orientation issues. So, and not in a good way. I mean, I know it's a knot theory seminar, so
yeah.
We all like knots, right? I mean, but not that kind. Okay, now I'm standing in front of this thing, but this is not really super clear why this is an invariant, so that's a bit of a miracle. It has to do with Rochlein's theorem. Maybe this signature over 8 you recognize from the Rochlin theorem, and it has something to do with the Cab-Ziemann. But I guess I wanted to. I'm sort of trying to build up to tell you about these examples, which I think are cool. But I just wanted to give you the background. Otherwise, they seem like they come out of nowhere. So that's why I wanted to sort of say the statements of the theorems. Although I realize that takes a little bit of time. Are there any more questions about any of this before I move on? So what's cool about, so my 2 examples are going to be, I'm just going to keep going. X1 is E connects on E, and X2 is going to be this thing, which I need to tell you about, called star E connects on star E. So, and what's good about these is that, well, they both have Kirby-Zeeman invariant 0. I mean, this is definitely a smooth manifold. These 2 individually have Kirby-Zeeman invariant 1, but when you sum them up, they get Kirby-Zeeman invariant 0. So that's true, and they're also homotopy equivalent. So they've got this. They've got the same. They've got an isomorphic quadratic 2 types, but this S of x1 alpha 1 is 0, 0, and x goes to alpha 2 is 1, 1. So they are not. So they're not even they're not homeomorphic, and in fact, they're also, it turns out they're also not stably homeomorphic. Which means that there does not exist a K such that if you take the connect sum of both of them with that many copies of S2 cross S2, you get a homomorphism. So even after adding S2 cross S2s, there's never going to be. This is something that people look at, is the question of stable classification of four manifolds. That's a separate topic, but it's sort of interesting to know about these manifolds, that they're homotopy equivalent, but they're not even stably homeomorphic. And these examples, so they were initially described by Teichner in the 90s. But what's interesting, well, I like them because, from the context of this talk, because while they fit into the theorem, they're the homotopy equivalent, but not homeomorphic. And then the key sort of well, the other key thing is I want to prove that that this is actually a smooth manifold. So they're both, so not only are they have these core properties, but they're both smooth manifolds. I can construct this manifold with a sequence of smooth maneuvers that don't require any use of the disk embedding theorem, Friedman's disk embedding theorem. So I sort of we initially knew that these manifolds existed using the disk embedding theorem, but we can now construct them from a purely kind of elementary maneuvers.
Excuse me.
Yes.
Sorry, I have one question. Here you said, in fact, they are not stably equivalent, stably homomorphic.
Yes.
That fact also can be shown by your theorem.
I mean, yeah, not by the theorem directly, but one would have to do some extra work to prove that the invariant S is actually a stable invariant.
Oh, okay.
But that's not clear. But I'm not saying that's clear. I mean, I mean, one has to. Yeah, there's a whole sort of extra story to understand the stable classification, involving computing borders and groups. So I wasn't going to go into that, but it doesn't follow from the theorem. It's just an extra fact.
Okay, thank you.
So what's this E? So I need to tell you. So E is a well, first of all, it's an S2 bundle over RP2. And it's one of the famous ones. There's not so many of these things, and if you require that it has orientable total space, then there's only two such bundles up to isomorphism, and this is the one with W2 is, if I then say W2 is non-zero and W2 of the universal cover is 0, then that fixes. There's once you have orientable total space, there's one where it has spin. It's a spin manifold, and there's one non-spin one, but the universal cover is spin. And it's famous because there's a picture of it in Gomp and Stipchitz. So it looks like this. I draw. This, and then this has a little circle around it, and that has to get a 1. Union a 3 handle, union 4 handle. So there's a curvy picture for this four manifold. That's So I'm just trying to make it visible, as easily visible as possible on the blackboard. So that's yeah, that's what E is. And then I was going to tell you about what this star partner is. So so given an E, you can make a star partner as follows. So star E. I mean, now obviously given E, I can take it to connect sum with itself. But then so star E is defined by the requirement that if I add CP2 to it, I get you connect some star CP2. So the first thing we have to know about is this star CP2. This is so Friedman wanted to call this the Chern manifold. I don't think it's got anything to do with Chern per se, just that's what Friedman wanted to call it. And it's, I mean, it's a full manifold that has its homotopy equivalent for CP2, but its Kirby-Siebmann invariant is 1, so it's not smoothable. To understand what it is, so how to construct it, so CP2 is given by adding this 2 handle and then union a 4 handle. So this gives me CP2. I add 2 handle, 4 handle, very standard. And then star CP2 we can make by making a trefoil with framing 1 and attaching it to the 4 ball. Actually, here at this point, I could use any knot with ARF invariant 1. So if I use ARF invariant 1 here and attach it with framing 1, and then the fact is that when I do that, the outcome has boundary. If I attach a 2 handle to the 4 ball like this with framing 1, the boundary is a homology sphere. And one of Friedman's big results is that a homology sphere is the boundary of a contractible topological manifold. So this bounds some contractible full manifold, and the union is this star CP2. So this part is a smooth part, and then this part is going to be very non-smooth, whereas here we have all smooth. So sort of you can't cap it off with a 4 ball, but you can cap it off with some contractible thing instead to get a closed manifold. And so once you know about the existence of this star CP2, you take your E, you add it on, you get this other manifold, and then in here somewhere you have to find a if you have a 2 sphere in a 4 manifold where the normal bundle has order number 1, then that's the same as a CP2 connected summand, because the boundary of a regular neighborhood of that thing will be an S3. So it'll just be like having a summand, and then you remove that thing and glue in a 4 ball, you just blow it down, and the result is the star E. So that gives you a construct. I mean, I haven't told you how to take this thing and then to find this embedded S2 with the right property. I'm going to tell you how to do that in a different setting, but that's the procedure for getting this star E. It's the thing that when you well, I mean, it's not always that. It's a little bit of a annoying notation, because in some circumstances that's a unique thing and some it isn't. In this case, this uniquely determines star E up to homeomorphism. But life isn't always that simple. Then you get this. Okay, so this is the way of getting this manifold. I assert that in this case that does uniquely determine a new manifold called star E, and then we take 2 copies of itself. But to do this construction used a lot of topological machinery. in order to define the star E, we had to use Friedman results, sorry, star CP2, and also in order to embed the CP2 in order to blow it down to get back to the star E, we also have to use the disk embedding theorem. So it's very the a priori definition of this star E is using many times the disk embedding theorem. So that's why we thought it was cool to be able to say that we could do this construction of the, not of the single one, but of the double one, with star E and it's star E. It's a smooth structure. So, I'll mention something about how we do this, then I'll pause. So we start with it involves CP2s again. So we take E, connect some E. We know that manifold very well. It's a nice smooth manifold, and we take a connect sum with CP2. And the aim is to find an embedding. So similar to before, CP1 in let's see, this manifold. I call this X hat just because I wanted a name for it. So I want to find an embedding of CP1 in there, which is homotopic to the original CP. I mean, there's a standard CP1 in here, and so I find one that's homotopic to it, and then blow down yields. We're going to do this in such a way that it yields star E, connect some star E. And what it's going to do is it's going to yield some smooth manifold, and we won't know what it is a priori, but then we'll be able to show using our classification that it actually is homomorphic to this one that we wanted. So whereas sort of, if you think about it, if you start with E connects M E and you want to get on to here, you have to sort of add on 2 star CP2s and then do some maneuvers to each of them and then blow down and get 2 CP2s and blow them down and you get this one. I'm just saying do this procedure over here twice. But what we're trying to do is just take 1 CP2 and do the procedure all in one go to the double thing, and the fact that you do it so that you can do it in an entirely smooth way. So that's the idea of the proof, and then with a smooth structure. Okay, so now I've been talking for about an hour, so now you guys have to tell me what you think. I mean, I could stop here and just and leave it at that. I suppose it depends on your how much you really want to know about the anybody who's interested could listen to the rest of it where I'll explain the details of this.
If you don't mind, may I ask you to tell us some details a little more?
So this is the bit which is for you really, Seongjong, where I thought I'd try and do some geometric arguments involving the involving Joule spheres and Whitney disks and so on. But but I wanted to give the background. All right. So are there any questions about what I've said so far? Before I launch into specific 4D arguments. I think it can be done in 10 minutes. For the one, that should be the one. That should be the 0. So here's my manifold X X hat. The connect sum of a copy of E and another copy of E and a CP2. And there's some 3 and 4 handles as well, some 3 handles and a 4 handle that are not mentioned. And this green disk here, this is what I've been calling CP1. Right? If I cap this off with the core of the 2 handle, then I get the CP1 in CP2. And so this is the thing I want to manipulate. I need to take this CP1 and I need to move it around to get back to another embedding that's supposed to be a more interesting embedding. And so if I'm going to do a homotopy, actually I'm going to do a regular homotopy. It's going to be some finger moves and then some Whitney moves. So finger moves means I'm going to take this thing here. I'm going to take a couple of little discs out of it, and then I'm going to tube them off. And what's going to happen is they're going to tube off around here. They're going to go around this pi1 element. So they're going on a big loop in the manifold around this order 2 element here. And then it's going to come back to itself. And this, you're supposed to imagine pushing this with your finger. That's why it's called a finger move. And then you push it back through itself. And when you push it back through itself, it gets 2 intersection points here and here. And then there's some auxiliaries data that you get a little Whitney disk here. And this is a disk such that if you used it for the Whitney move, then you would here's the model picture of the Whitney move. So if you were to now use this disk to guide a Whitney move, pushing this where the fingers pushed it back up, you push it back down and remove the intersections. So we just remember this blue disk as being the thing that you. This is one of the things you get from doing a finger move, and then we do the other finger move over here, where it goes around this one, and then also back up through here. So this is supposed to be a sort of schematic of doing these finger moves, where you take this thing and you push it around. And the only thing that's missing is I've just drawn, as we get here, we can think of this as a tube. And that could be sitting in this 3-dimensional slice where the picture's drawn. But as we get close to here, then we can only draw this a line's worth of the tube, and some of it has to happen in the past and the future, in the 4th dimension. in this manifold. We draw this picture in a three-dimensional sort of slice, an S3 sitting in the manifold. But there is of course the fourth dimension as well, and so some of this stuff will have to appear in the fourth dimension. So so far it's a realistic picture, minus some of the tube had to appear and go into the fourth dimension forwards and backwards near where this self-intersections are. So that's the start of our homotopy. We do this. We do these finger moves, and then we have to find. We don't want to just use these Whitney disks. We want to use some different Whitney disks, and if we then do a Whitney move using those, as I drew here, that will give the rest of a homotopy, and then we'll get an embedding, which will be the second embedding that we wanted. Okay, so I have to draw this. So the next thing I draw is I'm drawing the pre-image. So this is supposed to be our CP1, and this is now, after we've done the finger move, this is immersed into X hat. So the green thing, it's capped off with the core of this two handle, and it's immersed. And what that means is we've got these double points, and so this one, when you map it in, will be identified with this one, and this one will be identified with this one, and this one will be identified with this one, and this one with this one. So you get 4 double points, which is the 4 red dots in this picture. In the pre-image, it just looks like this, and the boundary of these disks, the disks don't live in the green, the disks just live in X, but the boundary of them is given by these arcs. So we have some arc here and here, and then when you map those in, they give a circle, and those 2 arcs, when you map those in, give another circle. So that's the pre-image picture. And maybe it's worth pointing out that if I were to take this orange line and look where that maps, that's going to map to something here that goes around the meridian of the dotted circle. So this maps to the meridian of the dotted circle over here. Okay, so there's this cool trick, which is due to the Stong, Richard Stong, not the one from Notes on Cobordism Theory, the other Stong, and what you do is you take these alternative Whitney arcs. So they go like this, and I do this for both of them. And notice that when I map this in, this still maps to a circle, because I go along here, and then that gets identified with here, and then I go along here, and that gets identified with here. So these still get mapped to a circle, and so does this. And so now this has a cool property that since this dotted line here goes to the meridian of the dotted circle, here what we've done is we've gone there, and then we go down that way, then we get identified here, then we go down again. So we've sort of gone twice around homotopically, we've gone twice around this thing. But going twice around this thing is null homotopic because we've got this two handle with the sort of this, you sort of see an RP2 sitting in here. If you fill this in with a Mobius band, this is telling us that going twice around here is null homotopic. I mean, this is the fundamental group is supposed to be a Z2 star Z2. So this meridian is order 2. So these are both order 2. Well, these are both null homotopic. Once was so these are null homotopic. So they bound some new disks, and actually they're actually null homotopic via a disk in. I mean, remember that the E was a bundle over RP2, and this bundle it's a non-trivial bundle, but it does admit a section. It was a non-trivial. So we have this. We have an RP2 sitting inside of here, which you can see from the Mobius band here, union the core of this.
Bisection. Bisection. Do you mean thinking of E as a complex two-dimensional line bundle that has a section and then?
I would think of this. It's quite helpful to think of this as think of an R3 bundle.
R3 bundle, yeah, sorry. Yeah. And then yeah. So you're finding a section of that. Okay.
Yeah. So it doesn't mean it's a trivial bundle, it just means
right.
It's a section. Yeah.
But after you have that section, you should have another line bundle that is twisted.
Yes.
Okay. All right. Thank you. That helps.
Yeah, good. Yeah, so thanks a lot. So there's and yeah, okay. So I mean, I get what we just need is that there is this RP2 embedded in here, and we can sort of use the 2 cell of this RP2 to find these Whitney disks. So these are going to be new Whitney disks. So we get new Whitney disks. But they have with +1 framing. So so here's sort of the procedure for constructing the new boundaries of the Whitney disks, and then they are null homotopic. I mean, the boundaries are null homotopic, so we can make them, and I claim we can actually make them be embedded, but they have this big defect that their framing is non-trivial. So what that means is if you want to do the Whitney move, you need to take a section of along your Whitney arcs, where along one of the arcs it's tangent to one sheet and then it's normal to the other sheet. And you need this. This is a section of the. We've got some disk, and it's a section of the normal bundle of the disk, and we need this section to extend to a non-vanishing section in order to do the Whitney move, because that lets you take 2 parallel copies of this disk that are disjoint, and then you can use those to. I mean, I guess another way of thinking about it is to cut out this little letterbox and then sort of push it up using the disk. And for that to be done in a way that everything's still embedded, you need to have disjoint copies front and back. So so you need that section to extend to a non-zero section. But in general, in this case, the framing is +1, which means that if you try and extend this section over the disk, it will have algebraically 1, 0. So that's bad. It means you can't just use them for for the Whitney trick straight away. So what are we going to do? Oh yes, I'm going to redraw the setup. So just focusing on what's happening with this this green sphere. So we had the green sphere, and then we did some finger move of it into itself. Like this. And then we have these Whitney disks. So I call this one W1 and this one W2. And then I just erased the picture, but when if we think about the picture of E again, then when we have this RP2 that's sitting here, the RP2 also has it comes with it has a dual 2 sphere. So here, this thing here gives me a dual S2. And this dual S2 is framed and embedded. So it's really useful. And it intersects this RP2 exactly once. Well, if it intersected the RP2 in one point, and we just use the RP2 to make the Whitney disk, it now intersects the so I get an S1 and S2 dual 2 spheres. It now intersects each of these Whitney disks in exactly one point. So that's a very rare thing in four-dimensional topology, but that's the fact that we have that is what enables us to do things smoothly in this case. But then we just have to, I mean, we say, okay, these were twisted Whitney disks, the framing wasn't right, so we can do an operation called boundary twist the WIs, and that gives us zero framing. This is a way, so but nothing comes for free when you do a boundary twist. This is an operation that's, by the way, described in chapter 1 of Friedman Quinn. Near the boundary of the disk, you replace this little strip here with some kind of twisted strip, and it changes the number of zeros of a generic section algebraically, but it does also introduce an extra intersection point of the Whitney disk with one of the base surfaces. So this thing, this thing I wanted to call F, but we also get a new WI intersect F intersection. So that's bad, but well, wait, what happens? Oh yeah. There's one more bit of data that this thing had, is that it also has so this thing here came from the CP1, and CP1 has framing +1, which means that it also has a dual sphere. You take the dual sphere and you push it off. So this it also has a dual sphere, but it's a twisted dual. So it's embedded. So this is a twisted dual S2. So the way where this comes from is you take your CP1 that you originally had, you push it off along a non-vanishing along a section, but the section will have 1, 0. So it's like any two any two copies of CP1 and CP2 intersect in a point, and that's what this point is. But this gives you some dual sphere to this thing. So we tube. Whenever we have a dual sphere, we can tube into it. So tube the WIs into G. So now WIs intersect F is empty. But we get some we get one more issue, which is that the WIs now intersect W1 intersects W2 because G intersects a parallel copy of G. So because this was a twisted dual, if I take a parallel copy, it intersects. So if I tube W1 and W2 into it, then I use two parallel copies of G, and they're going to intersect. But now we tube say W tube those into S1 and S2 as needed to remove any intersections. I guess I could just tube W1 into S1, and now get the W lines are embedded disjointly, and so use them for the Whitney disk, use them for the Whitney trick. And then we get this new CP1 in X tilde implies that X tilde equals some X prime connect some CP2, and then blow down and then show that in fact X prime is homomorphic to star E connect some star E. So what one has to do then is actually compute the invariance on this manifold to prove that they're equal, which I'm not going to do. So that's what you've got to do, and that is the end. So the final. So this part is not at all obvious, but that's what you have to do. So there's a lot of tubing around. You get these Whitney disks, then they're wrong, so you fix them up in one way, but you fix them up in one way and you make intersections, and then you tube the intersections around, and that fixes some other things, but then you get more problems, but then you just keep tubing into all the different things that are available. And because in the end, because we still always have these blue dual framed embedded spheres in reserve, at the end we can use those to fix everything up and actually get smoothly embedded Whitney disks, and then we do the Whitney trick. So at no point in any of this did I appeal to any topological machinery. This was all smooth construction. So I liked it. Okay, that's the end. Thank you for listening.
Thank you very much for interesting talk. Are there any questions or comments?
I have a few.
Great.
So thank you. First of all, thank you for the talk. It was really nice. I really enjoyed it. So this is a real simple one. Is this paper on the archive yet, or is it?
No, it's not. The first one that I mentioned will be hopefully quite soon. The one with Jonathan Hillman, and the stuff that I'm talking about here with the smooth structure on star E plus star E, we have to actually write that. A bit slow.
And then, because you have an embedded sphere sitting there, it looks like the Cyber-Whitman invariants are just no way that there are no Cyber-Whitman invariants for it, or they're zero, right? Are these embedded spheres square zero?
They're square zero, yeah.
Yeah, so the Cyber-Whitman will not.
Yeah, although in a way it's not sort of. I mean, we already know that these things are not homomorphic and not stably homomorphic. So,
Right.
So I would usually think of using that to detect exotic phenomena, whereas this is. I mean, I don't know if this is not universal in topology, but at one point Gompf said, let's call things fake if they're homotopy equivalent but not homomorphic.
Right.
So this is like a fake thing as opposed to a.
But like I'm thinking just in terms of like I don't know, connect summing it with stuff, right? Like if you start to try to build like other types of exotic phenomena, you're still kind of stuck in the water because there's no even after maybe trying to connect some with some other type of manifolds, you still have these spheres sitting here. So
Yeah. Oh, yeah. I don't know. Yeah, I don't know about using this to get exotic phenomena. I mean,
so
I
so the
think of
other
it as somewhat distinct from exotic phenomena personally, but
well
to ask.
so that I agree with you. I totally agree with you. But the kind of final question, which is, have you looked at the Bakor, Stipschitz, and Szabo's paper on smooth structures on four manifolds with finite cyclic fundamental groups? And if you have, can you tell me how you see these things differing, or maybe the same, or?
I mean, I think that I can't. Have I looked at that? I'm not sure I know exactly which paper, but I suspect that it's one.
Last year, I think.
But I think that's about sort of classifying. That's probably about exotic structures on such four manifolds.
Right.
So again, they're probably interested in things that are homomorphic. But
Yeah, I think the trick is, I asked about this earlier, like you get stuff that's homeomorphic, and then you can show that there's like an infinite number of non-diffeomorphic, and then you just get into a list of all possible things that can have, say, pi1 equal to z2 or pi1 equal to z2
oh yeah,
something.
so they were applying to Hamilton. So Hamilton and Craig had a long time ago had a classification of they had a homomorphic. I didn't go into the history of homomorphism classifications, but they did a homomorphism classification of four manifolds with pi1 z mod n. So I think in that paper they were applying this Hamilton Craig result. So
Yeah,
yeah, one of the things from today was trying to extend the known homomorph. This is one of the yeah, it's just like there's been certain results on homomorphism classifications in terms of like quadratic 2 type plus some extra data, maybe. Usually the extra data is like something about the second Stiefel-Whitney class. So yeah, one way of viewing that result is sort of extending those to another group. Unfortunately, not an infinite family of group. I mean, for the infinite family of groups, we could do the homotopy classification, but then it was just one extra group where we could do this D infinity, where we could do the homomorphism classification. So one could now ask for exotic four manifolds with D infinity.
right.
But I mean, I sort of think, you know, diffeomorphism implies homeomorphism implies homotopy equivalence, and a lot of these kind of papers are about the difference between these, whereas this is about this difference. So that's what I mean, and then just finding showing the interesting examples in here actually admit a smooth structure.
No, it's cool. It's cool.
I
see the difference, and just wondered if you had thought about just like, because it looks like what they're doing is jacking up the total number of like that there's just an infinite number of non-diffeomorphic stuff laying around, and then you use the classification of Hamilton and Craig.
That's right. I mean, I think it's a conjecture that basically every single homomorphism type has infinitely many smooth structures. So one would imagine that it could everywhere, but the way that people prove it is sort of bit by bit, because no one knows how to do it in general. And of course, you need to, in order to prove that, you need to know the Poincare conjecture in particular, or that it's false. That is the falseness of the.
I used to ask my advisor Ron Finchel if he thought
yes, I see. Finchel was your advisor. I see. Yeah. Well, he would have thought about that conjecture.
Oh yeah, definitely. And
he probably made it.
Well, I'd ask him every week, you know, like, do you believe it this week? And he'd flip a coin, go, nope, not this week. Next week, yep, I believe it this week. It's such a hard problem. So
yes, yeah, so. No, it's not. So indeed, but not really something I'm yeah,
No,
come up
no.
to think from this,
No,
but
I mean,
yes,
you got to do, this is part of the work of understanding all of this. So it's worthwhile, totally worthwhile.
yeah, I mean, the hope when one proves a topological classification is that someone will come along and use it for a smooth thing in the way that these guys did recently but there's a gap of 30 years.
Yeah.
Is that cool?
Yeah, that's like par for course in this type of stuff.
Yeah.
Well, thank you for the talk. Tell Brendan and Tara I said hi.
Will do, yeah. Thanks for the questions.
Yeah. Thank you.
Okay, are there any questions? Excuse me, I have one question here. First question is for curiosity, is there can we draw Kirby diagram for star E?
No, I don't think so. Not at least not in a well, there's different ways of answering that question. So I think that is a very good question. If it's a topological manifold where the Kirby-Zeeman is non-zero, then you can't draw a Kirby diagram for it in the strict sense.
Mm-hmm. So
because it's just, I mean, a Kirby diagram describes a smooth form manifold.
Yeah.
So the straightforward, but let me just sort of answer a couple of other questions you could have asked. Another question would be, can you draw a Kirby diagram for this one? Now that we've proved it's a smooth one, and I don't know. I mean, well, yes, there is a Kirby diagram for it, obviously, but I can't draw it. I don't know what and I think that's a very good question, and I would like to know what the Kirby diagram is, just because it's like when you have a cool. I mean, I think it's a cool form manifold. It has this nice property that it's a fake part of a fake pair, and we know the Kirby diagram for the E plus E, so it would be nice to just be able to say, look at this diagram. Here it is. Here's a picture of it. I mean, just for I don't know if such things have value, but oh yeah, there's one thing that the TQFT people like to look at, like to try and have things to test their invariance on, and it's important for them that they have things that are not stably homeomorphic. For some reason, to do with the value being of your invariant being invertible on S2 cross S2. And so this is, I think, a potentially interesting example for as a test case. So it would be nice to know a Kirby diagram for this thing. There's a third question: is could you draw a nice Kirby diagram of the smooth part and then just have the outcome be as an integral homology sphere that you then cap off with an unknown contractible thing? And that would be a reasonable definition of a Kirby diagram for a topological form manifold. It would be a Kirby diagram starting with the four ball going up to a homology sphere, and then you cap off with some unknown contractible thing. I don't know the answer to that either, but I would like to know what the Kirby diagram is for that, just the starry bit. And I don't. So that is it. That's sort of an interpretation of your question, not in the strictest sense of Kirby diagram, but in what I would say is a reasonable expansion of the notion of Kirby diagram to topological manifolds. You have as much of it to be smooth as possible. It's an open question whether every topological manifold can be written as a smooth piece plus a contractible. So I don't even know whether that's possible, let alone being able to draw a diagram of it. But I would very much like to know. So I think those are good questions.
Thank you very much. Okay, are there any more questions or comments? Okay, if not the case, thank you very much. Really interesting talk. Thank you very much.
Thank you very much for your attention.
Oh.
And